I'm Robert Sebastian, and this is Dreamtime Digest. Tonight, we'll explore the fascinating world of probability, a concept that quietly shapes the fabric of our everyday lives. As you drift into a state of relaxation, let your thoughts gently follow the path of chance and uncertainty, like leaves floating down a calm river. Probability. It's a concept as old as time itself, quietly guiding our decisions, even when we don't realize it. Probability, at its core, is the study of uncertainty, of measuring the chances that one thing might happen over another. It offers a sense of structure in an otherwise unpredictable world. Imagine rolling a die, for example. The likelihood of any one number landing face up is a 1 in 6 chance. That's probability in its simplest form, giving us a way to think about the unknown, a soft hum of order amidst the randomness. As we dive deeper, probability becomes more than just a mathematical abstraction. It starts to shape the way we perceive events around us. The roots of probability run deep, stretching back to the musings of gamblers and philosophers alike. Over time, we've refined this understanding, recognizing that every outcome, no matter how trivial, has a chance tied to it. But it's not just games of chance that rely on probability. Oh no, it weaves its way into weather forecasts, medical tests, and even the way we cross the street. Probability provides the structure by which we navigate the uncertainties of our everyday lives. Now, let's explore the concept of experiments, the very heart of probability. An experiment in this context isn't a test tube bubbling away in a lab, but rather any process that can result in one or more outcomes. Flipping a coin, drawing a card, rolling a die, these are all experiments. Each has a set of possible results, called outcomes, that give us something to measure. The beauty of probability is that it allows us to predict these outcomes, not with certainty but with a degree of confidence. It's like knowing which way the wind might blow, even if you can't feel it just yet. And here's where we introduce events. Events are collections of outcomes, little clusters of possibilities. Picture rolling a die again. Getting a number higher than 4 is an event comprised of the outcomes 5 and 6. The more we think about events, the more we understand how probability links them together. When we consider that every experiment can lead to multiple events, probability becomes our tool for deciphering the patterns that emerge from seemingly random moments. But the question lingers: how do we connect these events? How do they relate to one another? This is where the rules come into play. Probability has a few key rules that help us connect events. Let's start with the addition rule. It tells us that if two events are mutually exclusive, meaning they cannot happen at the same time, like rolling a 2 or a 3, on a die we simply add their probabilities together. Simple, but powerful. It's a way of giving weight to multiple possibilities. But what happens when events overlap, when they share an outcome? That's when we must subtract the overlap to avoid counting it twice. The precision of probability shines in moments like these, quietly balancing all possibilities. Equally important is the multiplication rule. This one speaks to the relationship between events that happen in sequence. Think of it like flipping a coin and then rolling a die. The probability of getting heads and then a 6 is found by multiplying the chances of each event. It's a methodical process, one that mirrors life's own chain of actions and consequences. And yet, probability doesn't end here. These rules help us understand how different possibilities merge, but they also lead us into the concept of complements. For every event, there's a complement, the possibility that the event won't happen. Imagine tossing a coin and asking what the chances are that it won't land on heads. That's the complement at work. It's the opposite side of the coin, both figuratively and literally. Complements remind us that every event, no matter how small, exists within a larger framework. If something doesn't happen, something else does. This balancing act of probability feels rather like the natural ebb and flow of life itself. One path closes, another opens. The elegance of complements lies in their simplicity, quietly completing the circle of outcomes in our minds. Now, we shift to the concept of conditional probability. This is where things become a bit more intricate. Conditional probability is about refining our predictions when we already know something has happened. Imagine you're holding a deck of cards, and you know the top card is a heart. What are the chances it's also a queen? Conditional probability guides us through these kinds of questions, recalculating the odds based on what we already know. It's a way of narrowing the possibilities, trimming away the uncertainty one fact at a time, much like a sculptor reveals the form hidden within marble. Bayesian probability takes this concept even further. It allows us to update our beliefs as new information comes to light, continuously refining our understanding of the world. As we gather evidence, Bayesian thinking shows us how to adjust our probabilities, ensuring our predictions become more accurate over time. This method is particularly useful in fields where uncertainty is the norm, whether we're diagnosing medical conditions or predicting market trends. It reminds us that knowledge isn't static, it evolves, and probability evolves with it, shifting and reshaping as new evidence emerges. Finally, we find ourselves arriving at the grand concepts of the law of large numbers and the central limit theorem. These are the guiding stars of probability, offering us insights into what happens when experiments are repeated many times over. The law of large numbers tells us that as we conduct more trials, the outcomes begin to mirror the expected probabilities. It's like tossing a coin 1,000 times. Eventually, heads and tails will balance out. The central limit theorem reveals that when we average the results of many trials, the outcome tends to form a bell curve, clustering around the middle. Both concepts show us that even in the unpredictable realm of chance, patterns emerge. Probability offers us a way to glimpse the underlying structure of the world, a way to see the shapes that randomness carves out over time. And so, probability isn't just about numbers or chances. It's a lens through which we view life's uncertainties, an ever-present guide that helps us make sense of the unknown, offering clarity, one possibility at a time. Next up are random variables, those curious creatures of mathematics. They appear where uncertainty lingers, translating the unpredictability of life into the language of numbers. A random variable is not a variable in the ordinary sense, rather it is a function that assigns numerical values to the outcomes of a random process. You might think of it as a bridge between chance and the precise world of mathematics. Picture a coin flip, a simple act. And yet, beneath that spinning coin lies a random variable, silently assigning a number to each possible outcome, heads or tails, 0 or 1. And just like that, the chaos of randomness starts to find structure. But what makes a random variable so useful is that it transforms randomness into something we can measure and understand. By assigning numbers to outcomes, we can apply the rules of probability to make predictions even when we don't know exactly what will happen. It's rather like navigating a foggy night with a lantern. Although you can't see everything, you gain just enough clarity to make your way. In probability theory, this concept is not limited to coin flips alone. Whether you roll a die, draw a card, or observe the temperature, the random variable is there, casting light on what might otherwise be uncertain. Now, random variables come in two varieties, discrete and continuous. Discrete random variables are those that take on specific, countable values. Think of rolling a die here. The possible outcomes are finite, and the random variable can only take on the values 1, 2, 3, 4, 5, or 6. Each outcome is distinct, like stepping stones across a river. The space between each stone is clear and unbridgeable. You know exactly where your foot will land, even though you don't know in advance which stone you will step on. It's this clarity of possibility that makes discrete random variables so tangible and easy to grasp. On the other hand, continuous random variables flow more freely. Instead of distinct steps, imagine wading into the river itself. You can stop at any point, at any depth. A continuous random variable takes on an infinite number of values within a given range. Consider measuring the height of a tree. Its height could be anything within a span of possibilities, and there is no clear separation between one possible value and the next. Continuous random variables remind us of the fluid nature of life itself, where outcomes are not always distinct, but blend into one another like the colors of a sunset. With these types of random variables in mind, we then encounter the concept of probability distributions. A probability distribution is like a map that tells us how likely different outcomes are. For discrete random variables, the probability distribution shows the likelihood of each possible value. For instance, in our die rolling example, the probability of rolling a 4 might be 1 in 6. Each possible outcome has a probability, and when all these probabilities are laid out, we begin to see a fuller picture of the random process. It's as though we are piecing together a mosaic, each tile representing a different possibility. Continuous random variables, however, require a different approach to probability distributions. So instead of assigning probabilities to individual outcomes, we look at the probability that the variable falls within a certain range. Since there are infinitely many possible values, the probability of any one exact value is essentially zero. Instead, we focus on intervals. For example, if we are measuring rainfall, we might ask about the probability that it will rain between 2 and 3 inches. This shift from points to ranges allows us to navigate the fluidity of continuous random variables without losing our sense of direction. Another key concept tied to random variables is the expected value. The expected value, often referred to as the mean, is a measure of the central tendency of a random variable. It tells us where we might expect the outcome to land, on average, over many repetitions of the experiment. For discrete random variables, we calculate the expected value by multiplying each possible value by its probability and then summing these products. The result is a weighted average, guiding us toward the heart of the distribution. It's a bit like predicting where a dart might land if we threw it hundreds of times. While each individual throw may vary, the center of the target remains consistent. For continuous random variables, the process is similar but involves integrating the probability density over the range of possible values. The expected value still serves as a beacon, offering insight into the central tendencies of the data, even when the outcomes flow across a continuous spectrum. Expected value teaches us that while randomness may seem to scatter outcomes unpredictably, there is a pattern hidden within the chaos, a steady pulse beneath the surface of uncertainty. Variance and standard deviation offer further insight into random variables, showing us not just where the outcomes tend to cluster, but how spread out they are. Variance measures the average squared distance of each outcome from the expected value, providing a sense of how much variability exists within the data. A low variance means that the outcomes hug close to the expected value, like a tightly knit family, while a high variance suggests greater spread, as if the outcomes are wandering further afield. Standard deviation, the square root of variance, refines this concept, giving us a clearer measure of this spread. Taken together, these ideas, random variables, probability distributions, expected value, and variance, help us make sense of the randomness that permeates the world around us. They give us tools to measure, predict, and understand outcomes that may seem entirely uncertain. Whether we are calculating the chances of rain, estimating the stock market's fluctuations, or rolling dice in a game, the framework of random variables helps us grasp the unpredictable with a bit more certainty. In closing, random variables aren't just a mathematical curiosity, they're a reflection of life's inherent unpredictability. Through them, we gain a window into the structure of chance itself, transforming randomness from something intangible into something we can measure and explore. And in that exploration, we find patterns, probabilities, and insights that guide us through uncertainty, giving us a clearer view of the world, one outcome at a time. These are the unseen architects behind much of our understanding of randomness and chance, shaping how we perceive uncertainty. The probability distribution, at its heart, describes how probabilities are spread over the possible outcomes of a random event. It's as if we are given a map, showing us which outcomes are more likely to occur and which are rare. The map, though abstract, reveals the landscape of possibilities before us. Imagine standing before a vast horizon, with each step representing a potential outcome and the probability distribution guiding us toward the paths that we're most likely to walk. For discrete, random variables, this distribution takes a familiar, countable form. Picture rolling a fair die. The probability of each number coming up is 1/6, and when we lay out all 6 possible outcomes, we see the uniform distribution each number has an equal chance of airing. The simplicity of this scenario hides the deeper truth. Probability distributions are everywhere, from the way traffic flows during rush hour to the number of phone calls a help desk receives in a day. Distributions provide a way to capture and describe the randomness we experience. They help us make sense of what might seem, at first glance, entirely unpredictable. Yet, not all distributions are so uniform. Life often deals in skewed probabilities, where some outcomes are more likely than others. Consider flipping a weighted coin, one that lands on heads more frequently than tails. Here, the distribution is uneven or skewed, giving more weight to certain outcomes. The beauty of probability distributions lies in their flexibility to capture both the fair and the biased. It's a reminder that life, too, is filled with imbalances, where some outcomes dominate while others remain distant possibilities lingering on the edges. These imbalances shape how we make decisions and how we anticipate what's to come. So now if we move from the discrete to the continuous, the landscape shifts once again. Continuous probability distributions handle situations where outcomes aren't confined to a finite set of values, but can take on any value within a range. Imagine measuring the exact height of a person or the temperature outside. In these cases, the possible values are infinite. Instead of assigning probabilities to each individual value, we consider ranges. What's the probability that the temperature will fall between 18 and 20 degrees, for example? It's like painting with a broad brush, smoothing over the gaps between outcomes and focusing on the likelihood of landing within a particular interval. One of the most well-known continuous probability distributions is the normal distribution, often recognized by its bell-shaped curve. This curve has a beautiful symmetry, peaking in the center and tapering off smoothly on either side. It's a distribution that frequently appears in nature, describing everything from human height to the daily temperature. The majority of values cluster around the mean or average, with fewer and fewer outcomes as you move away from the center. It's a lovely representation of how in many areas of life, most things tend to hover near the middle, with extremes being far less common. There's a certain comfort in the predictability of this pattern. But probability distributions don't just describe what's likely, they also give us insight into the variability of outcomes. This brings us to the concept of variance. Variance measures how spread out the outcomes are on the mean. A high variance tells us that the outcomes are more widely scattered, while a low variance suggests they're tightly packed around the mean. In practical terms, this could represent the difference between temperatures that barely fluctuate over the course of a course, and temperatures that swing wildly from one extreme to the next. Variance shows us not just where we expect to land, but how far off course we might be. As we explore probability distributions further, we encounter the notion of skewness. While the normal distribution is beautifully symmetric, many real-world distributions are not. Skewness measures the asymmetry of a distribution. When a distribution is skewed to the right, it means that there's a long tail on the higher side of the curve. Think of income distributions, where most people earn within a certain range, but a few earn significantly more. A left-skewed distribution, on the other hand, has a long tail on the lower side, like the distribution of scores in a particularly challenging exam, where many students score low and only a few perform exceptionally well. Another crucial aspect of probability distributions is the concept of kurtosis, which tells us about the tailedness of a distribution, how heavy or light the tails of the curve are compared to the normal distribution. A distribution with high kurtosis, heavier tails, meaning that extreme outcomes are more likely. Conversely, a distribution with low kurtosis has lighter tails, where extreme outcomes are rare. This measure helps us understand the likelihood of encountering outliers, the unexpected results that fall far from the average. In life, outliers can be moments of surprise, events that challenge the norm, reminding us that sometimes the unexpected does happen. Probability distributions also find themselves intertwined with decision-making. By understanding the distribution of possible outcomes, we can make more informed choices. In business, for example, managers might use probability distributions to forecast sales, allowing them to prepare for various scenarios, whether it's a surge in demand or an unexpected drop. In medicine, distributions help assess the likelihood of treatment outcomes, providing doctors with a way to evaluate risks and benefits for their patients. These distributions act as a guiding light, helping us navigate the uncertainties that accompany every decision we make. In conclusion, probability distributions offer a framework for understanding the ebb and flow of chance. They give us a way to quantify uncertainty, showing us which outcomes are likely, which are rare, and how far from the norm we might find ourselves. Whether we're dealing with the finite world of discrete distributions or the infinite possibilities of continuous ones, these tools give us clarity in a world filled with unpredictability. They remind us that while randomness may seem chaotic, there are patterns to be found, curves to be drawn, and probabilities to be measured, guiding us ever closer to understanding the inherent structure of chance. Now let's move on to another topic. Bayes' theorem is a beautiful piece of reasoning that allows us to update our beliefs in the light of new evidence. At its heart, it's a method of adjusting probabilities when we acquire new information. This might sound rather abstract, but the concept is far more intuitive than you'd expect. Imagine you're a detective piecing together clues. Each new piece of evidence that comes to light helps you refine your understanding of the situation, allowing you to shift your suspicions toward one suspect or another. Bayes' theorem is the mathematical embodiment of that very process, taking what we already know and sharpening it with new insights. Bayes' theorem operates on the idea of conditional probability, or the likelihood of an event occurring, given that something else is already known to be true. It starts with a prior probability, our initial belief about how likely an event is. Then, as new data or evidence arrives, we adjust that belief to form what's called the posterior probability. This process is akin to navigating with a compass. We set off with a rough direction in mind, but as we encounter new landmarks or features along the way, we refine our course, adjusting to stay on the right path. It's a dance between the known and the unknown. The theorem itself is expressed in a simple equation, though the elegance of its meaning far outweighs the appearance of the formula. It tells us to multiply the prior probability by the likelihood of the evidence, and then divide that by the overall probability of the evidence occurring. The result? A more accurate estimate of how likely the event is, given what we now know. Bayes' theorem therefore transforms probability from something static into something dynamic, constantly evolving as new evidence emerges. It reminds us that knowledge is never fixed. It is a living, breathing thing that grows and shifts with each new observation. One of the most compelling aspects of Bayes' theorem is its ability to handle uncertainty in real-world situations. For instance, in medicine, doctors often use Bayesian thinking when diagnosing patients. Let's say a patient comes in with symptoms that could indicate a rare illness. The doctor begins with a prior probability based on the prevalence of the illness in the general population. Then, the patient undergoes a test, which provides new evidence. Bayes' theorem helps the doctor refine their diagnosis by combining the prior probability with the likelihood that the test result would be positive if the patient truly had the illness. This isn't just about numbers on a page, it's about the practical use of probability to make informed decisions. In this case, the posterior probability tells the doctor how likely it is that the patient has the illness, given the test result. It's a method that goes beyond guesswork, offering a structured approach to reasoning under uncertainty. By allowing us to update our beliefs as more information becomes available, Bayes' theorem captures the essence of learning, constantly revising, constantly refining. Let's extend this thinking to another arena, weather prediction. Meteorologists start with models based on historical data. These models give them a prior probability for certain conditions, like the likelihood of rain. As they gather real-time data, barometric pressure, humidity, wind patterns, they can update their forecasts. The Bayes' theorem allows them to adjust their predictions in light of this new evidence. So, while they may have initially thought there was a 30% chance of rain, new data might push that probability up or down. It's a system of continuous learning, much like how we adapt our thoughts based on the world around us. Bayes' theorem also finds itself at home in the world of finance. Investors, for example, use it to adjust their expectations about the value of assets. Imagine an investor believes there's a 40% chance that a company's stock will rise based on market trends. Then new information comes to light, a favorable earnings report perhaps. This evidence shifts the investor's belief, and Bayes' theorem provides the framework for adjusting the probability. The investor can now refine their decision-making process, incorporating the latest insights to make a more accurate assessment of the stock's future performance. Even in legal cases, Bayes' theorem has a place. Think of a jury listening to testimony and examining evidence. They begin with a belief about the defendant's guilt or innocence, but each new piece of evidence adjusts the belief. Perhaps a witness testifies or forensic evidence is presented. With each addition, Bayes' theorem helps refine the probability of guilt. The process is akin to slowly bringing a picture into focus. Each piece of evidence clarifies the image until a conclusion becomes clear. Bayes' theorem is, in a sense, a guide to rational thinking, helping us navigate uncertainty with care and precision. What makes Bayes' theorem truly powerful is that it doesn't just stop with one update. It's a process that can be repeated over and over, allowing us to continually refine our beliefs as more evidence rolls in. It's the very model of adaptability. We start with a prior, adjust it with new information, and if more data becomes available, we adjust again. In this way, it mirrors life's constant flow of learning and adapting. The world is rarely static, and our understanding of it shouldn't be either. Consider how this theorem might apply to everyday life. You start with a hunch about how things might turn out, whether it's deciding whether to bring an umbrella or estimating how long it might take to drive to a destination. As new factors emerge, dark clouds gathering overhead, or news of traffic delays, you adjust your expectations. Today's theorem is there, in the background, shaping how you refine your decisions. It's a silent partner in our day-to-day reasoning, always at work, guiding us through the uncertainties of life. In conclusion, Bayes' theorem offers us a way to embrace uncertainty with a clear mind. It shows that our beliefs are not set in stone, but are meant to evolve with new information. Whether we are doctors diagnosing patients, meteorologists predicting the weather, investors making financial decisions, or simply navigating the twists and turns of everyday life, Bayes' theorem offers a structure for learning, adapting, and refining our understanding of the world. It's a reminder that with each new piece of evidence, we get a little closer to the truth. The law of large numbers. It sounds quite grand, doesn't it? Yet, its essence is beautifully simple, like the steady rhythm of waves on a shore. So at its heart, the law of large numbers tells us that as we repeat an experiment or process more and more times, the average of the outcomes will approach the expected value. It's a reminder that, while life may seem random in the short term, patterns emerge over time. Imagine flipping a coin. A single flip might give you heads, and another might give you tails. But flip the coin 1,000 times, and you'll find that the number of heads and tails comes remarkably close to an even split. This idea offers a kind of comfort. It reassures us that, given enough trials, chaos has a way of balancing itself out. In probability, we often work with theoretical expectations. For example, when rolling a fair die, we expect each number to appear 1/6 of the time. Of course, with just a few rolls, this may not happen. You might roll a 6 3 times in a row, or not at all. But as the number of rolls increases, the proportion of sixes along with the other numbers begins to approach that perfect, expected 1/6 distribution. This is the law of large numbers at work, guiding us toward equilibrium. It's important to recognize that this law doesn't imply that randomness disappears as we repeat an experiment. Quite the contrary, randomness is still very much present in each individual trial. What the law tells us is that, over time, the average outcome will converge on the expected result. It's like walking along a winding path that eventually straightens out. Each step you take may veer left or right, but if you continue far enough, the direction becomes clearer. The more trials you conduct, the less impact any single outcome has on the overall result, smoothing out the bumps of randomness. There are two versions of the law of large numbers, the weak law and the strong law. The weak law states that as the number of trials increases, the probability that the sample average deviates from the expected value by more than a small amount approaches zero. In other words, given enough trials, the sample average is almost certain to be close to the expected value. It's as though the law provides a gentle pull toward the expected outcome, gradually bringing the results in line with our predictions. The strong law, on the other hand, goes even further, asserting that the sample average will converge exactly to the expected value, given an infinite number of trials. Now, while the law of large numbers works well in theory, it's important to consider how it plays out in practice. In real-world scenarios, we rarely have the luxury of infinite trials. However, the law still holds significant value. It teaches us to trust patterns that emerge over time. In fields like insurance, finance, and even medicine, professionals use the law of large numbers to make decisions based on long-term trends. An insurance company, for instance, cannot predict when any one policyholder might file a claim, but by analyzing data from thousands or millions of clients, they can accurately estimate how many claims they'll face in a year. In essence, the law of large numbers helps us deal with uncertainty. When individual outcomes are unpredictable, the law offers a way to understand the overall pattern that emerges from many repetitions. It's a tool for making sense of the unpredictable, for finding order in what seems like chaos. Whether we're talking about the results of flipping coins, the behavior of financial markets, or the spread of diseases, the law reminds us that consistency arises over time, as though the universe itself bends toward balance. Interestingly, the law of large numbers also plays a role in everyday life, even if we don't consciously realize it. Think about something as simple as estimating the time it takes to commute to work. On any given day, traffic might vary. One morning you could breeze through without delay, another you might be stuck in congestion. But over the course of weeks and months, you begin to develop a reliable sense of how long your commute typically takes. This is the law of large numbers. In action, individual trips vary, but the average tends to settle around a predictable value. And yet, despite its elegance, the law of large numbers doesn't guarantee that we won't experience anomalies. It's crucial to remember that randomness can still surprise us, even after many trials. There's no magical force ensuring that outcomes align perfectly with expectations in every moment. The law simply tells us that, in the long run, the averages will behave predictably. It's a lesson in patience, in trusting that time reveals the true nature of things, even if the short term feels erratic or unexpected. This law also intersects with other fundamental principles in probability, such as the central limit theorem. While the law of large numbers assures us that the sample average will approach the expected value, the central limit theorem tells us that the distribution of these averages will form a normal distribution as the number of trials increases. It's a harmonious relationship, one law guiding us toward the expected result, and the other shaping the form in which these outcomes cluster. Together, they provide a fuller picture of how randomness resolves itself over time. In closing, the law of large numbers invites us to view the world with a sense of calm. It tells us that while life may throw us curveballs in the short run, there's a quiet order that emerges over the long haul. It's a reminder to step back and look at the bigger picture, to recognize that the patterns we seek often take time to reveal themselves. Whether we are rolling dice, analyzing data, or simply observing the world around us, the law teaches us that randomness, though unpredictable in the moment, has a way of bending toward balance in the end. The central limit theorem. It sounds quite grand, doesn't it? Yet beneath the name lies a remarkably simple yet profound idea, an idea that quietly underpins much of our understanding of probability and statistics. This theorem tells us that, under certain conditions, the distribution of sample means will tend to form a bell-shaped curve, known as a normal distribution, regardless of the original distribution of the data. It's a concept that emerges from the heart of randomness, revealing a pattern where chaos once seemed to reign. The more samples we take, the clearer this shape becomes, providing us with a sense of balance in the unpredictable world of chance. Imagine you're observing a process, perhaps something as simple as flipping a coin or measuring the height of individuals. Each time you perform the experiment, the result might differ. A coin flip gives you heads or tails. A height measurement may vary from person to person. But as you gather more and more samples and calculate the average of those results, something remarkable happens. No matter how the original outcomes were distributed, the averages of those samples will begin to form a normal distribution, that iconic bell curve with its peak at the center. It's as though the randomness of individual events begins to converge into something orderly and predictable. The central limit theorem offers us a glimpse into this balancing act. It tells us that even if the data we collect is skewed or even, the distribution of the sample means will smooth out over time, clustering around the average. This is where the beauty of the theorem lies. No matter how irregular the original data set, the averages will tend to follow the same predictable pattern. It's as though the universe itself has a way of ironing out the wrinkles in randomness, creating a steady rhythm amidst the noise. And this, in turn, allows us to make predictions and draw meaningful conclusions from even the most chaotic of data. One of the key insights from the central limit theorem is that this process works regardless of the shape of the underlying data. Whether we're dealing with data that's uniformly distributed, heavily skewed, or even wildly irregular, the theorem assures us that the distribution of the sample means will approximate a normal distribution as the sample size increases. The larger the sample, the more reliable this approximation becomes. It's a bit like seeing the stars on a cloudy night. The more clouds that drift away, the clearer the sky becomes, until eventually the full constellation emerges. This theorem also brings with it a sense of harmony between the individual and the collective. Each individual sample might vary widely, yet when we look at the averages across many samples, a pattern begins to emerge. It's a reflection of life itself. While individual moments may seem random and disconnected, when we step back and observe the broader picture, we start to see the patterns that shape our experiences. The central limit theorem helps us find that broader picture, guiding us to see beyond the randomness of individual events and toward the steady truths that lie behind them. Now, it's worth noting that while the central limit theorem applies to many situations, it does come with certain conditions. For the theorem to hold, the samples must be independent, meaning that the outcome of one trial doesn't affect the outcome of another. This independence ensures that each sample provides a fresh, unbiased glimpse into the data, free from the influence of prior outcomes. Moreover, while the theorem works with any underlying distribution, it becomes more accurate as the sample size grows. A larger sample size means the average of those samples will cluster more tightly around the true mean. Think of it this way. If you were to take only a handful of measurements, you might see some variation, some deviation from the expected average. But as you continue to gather data, those variations start to balance out, and the overall pattern becomes clearer. It's as though each new piece of information helps to refine the larger picture, slowly revealing the structure that underlies the randomness. This is the essence of the central limit theorem, the idea that by looking at the average of many events, we can cut through the noise and discover something reliable, something predictable. So this ability to smooth out randomness has profound implications in fields ranging from science to economics. In the world of finance, for instance, analysts use the central limit theorem to model stock prices, allowing them to predict future trends based on historical data. In medicine, researchers apply the theorem to study the effectiveness of treatments, comparing the average outcomes of patients in different groups. And in everyday life, the central limit theorem can help us understand everything from the fluctuation of daily temperatures to the variation in customer satisfaction at a restaurant. It offers us as a way to make sense of the world, even when individual events seem unpredictable. Another key concept tied to the central limit theorem is the standard error, which tells us how much the sample mean is expected to vary from the true population mean. As the sample size increases, the standard error decreases, meaning the sample mean becomes a more accurate reflection of the true mean. This is one of the reasons why the central limit theorem is so powerful. It allows us to make increasingly precise predictions as we gather more data, honing in on the truth with each new piece of information. The more we observe, the clearer the pattern becomes. In summary, the central limit theorem is a cornerstone of probability and statistics, offering us a way to navigate the randomness of individual events and uncover the patterns that lie beneath. It tells us that even when data appears chaotic, there is order to be found in the averages. Whether we are measuring human heights, predicting market trends, or analyzing scientific experiments, the central limit theorem provides us with the tools to cut through the noise and find clarity. It's a reminder that, while life may be filled with randomness, there is a deeper structure waiting to be revealed. Stochastic processes. The term may seem unfamiliar at first, but it describes something all around us, a world filled with unpredictability, where events unfold with an element of chance. A stochastic process is a mathematical way of modeling situations where the outcome is uncertain and depends on random variables over time. Think of it as observing the ebb and flow of a river, where each ripple and wave is part of a larger, evolving pattern of randomness. At its core, a stochastic process is a way of understanding how things change, not in a fixed, predictable way, but through the dance of probability. One common example of a stochastic process is something as simple as the fluctuation of stock prices. Each moment, a stock's price can rise or fall based on countless factors, many of which are unpredictable. Yet, through the lens of stochastic processes, we can begin to model and analyze these changes, providing a framework for understanding the patterns within the unpredictability. It's not about eliminating uncertainty, but about making sense of it, capturing the rhythm of change in a world where the future is never entirely certain. And this approach can be applied to countless other systems, from the spread of diseases to the behavior of particles in physics. At the heart of a stochastic process is the concept of randomness unfolding over time. Unlike a static event, a stochastic process is dynamic, evolving with each passing moment. Each step in the process depends, at least in part, on chance. And yet, over time, patterns emerge, small shifts and movements that, when viewed from a broader perspective, start to make sense. Take, for example, the path of smoke rising from a chimney. Up close, the swirls and eddies of smoke seem erratic, unpredictable. But step back, and you'll see the overall flow moving steadily upward, a process shaped by both randomness and structure. One particularly well-known type of stochastic process is the Markov process. The beauty of a Markov process lies in its simplicity. At any given moment, the future state depends only on the present state, not on the path that led to it. Imagine walking through a forest, where each fork in the trail represents a decision point. In a Markov process, your next step depends solely on the direction you choose now, not on the path you took to arrive at this fork. This property of memorylessness makes Markov processes particularly useful in modeling systems where the past is irrelevant to the future once the present is known. Markov processes are often used in a variety of real-world applications. Think of a game of snakes and ladders, where each roll of the die determines your next position on the board. The roll itself doesn't care how you got to your current square, it only dictates where you'll go next. Similarly, in finance, Markov models can be used to predict stock prices, where the future price depends only on the current price, regardless of the past trends. This elegant simplicity allows us to model complex systems without needing to track every detail of history, focusing instead on the present and the immediate future. Another fascinating type of stochastic process is Brownian motion, often referred to as a random walk. This concept originated from the observations of pollen particles floating in water, seemingly dancing in random directions. What was initially puzzling, the erratic movement of particles, became clearer when it was understood that this motion resulted from countless, tiny collisions with water molecules. Brownian motion is now used to model everything from the movement of molecules in a fluid to the fluctuations of financial markets. It's a vivid illustration of how randomness, while chaotic on the surface, often follows deeper, underlying patterns. Stochastic processes aren't just confined to the physical world. They also play a key role in biology and population dynamics. Consider the spread of a virus through a population. Each interaction between individuals carries a certain probability of transmission, making the process inherently stochastic. Yet, by modeling the virus's spread over time, we can predict how an outbreak might unfold, estimate the number of future cases, and understand how interventions like vaccinations might alter the course of the epidemic. In this way, stochastic processes offer us a way to grapple with the uncertainty of life, finding order within the randomness. Now, while stochastic processes might seem abstract, they are grounded in the idea of probability distributions. A probability distribution tells us the likelihood of different outcomes within the process. For instance, in Brownian motion, we can predict how far a particle is likely to move over a certain time period, even though we can't predict its exact path. In essence, stochastic processes give us tools to quantify uncertainty, helping us understand the range of possible outcomes rather than focusing on one fixed prediction. This is key to why stochastic processes are so useful. They offer a map of possibilities, even in a world filled with uncertainty. An important aspect of stochastic processes is their ability to model systems that evolve over time. Whether we're looking at the weather, tracking the growth of a company, or studying the movement of animals in an ecosystem, stochastic processes provide a way to understand how these systems develop and change. The randomness that drives these processes doesn't mean chaos, rather, it suggests that while individual events may be unpredictable, the overall behavior of the system can be understood and modeled. It's a reminder that randomness and order are not mutually exclusive but are, in fact, deeply intertwined. In summary, stochastic processes offer us a way to navigate the unpredictable currents of life. They provide a framework for understanding how randomness unfolds over time, whether in the rise and fall of stock prices, the spread of a disease, or the erratic path of a particle. These processes teach us that while the future may never be fully certain, we can still find patterns within the randomness, guiding us through uncertainty with the tools of probability. Stochastic processes remind us that, even in the most complex systems, there is always a way to find meaning, to make sense of the ever-changing world around us. Markov chains. The name may evoke something mechanical, yet these processes are deeply woven into the fabric of randomness. At their heart, Markov chains represent systems that evolve in a way that the future depends solely on the present, not on the past. Imagine standing at a crossroads with multiple paths stretching ahead. The direction you choose next doesn't depend on the steps you've taken to get there, but only on the position you now occupy. This idea of memorylessness defines Markov chains, making them a powerful tool for modeling situations where history is irrelevant once the present is known. Markov chains are, in essence, sequences of events. The outcome of each step depends on probabilities, but crucially, only on the current state of the system. Consider, for example, the weather. If today is sunny, Tomorrow's weather depends only on the fact that it's sunny or today, not on whether it rained 3 days ago. A Markov chain models this by assigning probabilities to the next state, whether sunny or rainy, based solely on the current condition. The concept may feel simple, but its implications run deep, touching fields as diverse as economics, biology, and even the movement of particles in physics. One of the striking features of Markov chains is how they encapsulate the balance between randomness and predictability. On the surface, the outcome of each step feels uncertain, governed by probabilities. And yet, over time, the chain reveals a hidden structure, a long-term pattern in the behavior of the system. This balance makes Markov chains invaluable for understanding systems that evolve over time, particularly when those systems are influenced by chance. Whether you're analyzing financial markets, studying population dynamics, or even modeling internet traffic, Markov chains offer a way to glimpse the underlying order in the apparent chaos. A simple illustration of a Markov chain might be found in a game like Monopoly. Each turn, a player rolls the dice and moves around the board, landing on properties with various consequences. The next move depends solely on the current position of the player, not on how they arrived there. Markov chains operate in much the same way. The current state dictates the probabilities of moving to the next state, with no memory of the steps that led to the present. This memoryless property makes these chains elegant and straightforward, while still being capable of modeling complex systems. There are several types of Markov chains, but two common classifications stand out: discrete time and continuous time Markov chains. In a discrete time Markov chain, events occur in distinct, separate steps. Think of flipping a coin. After each flip, you decide what to do next, with the probabilities assigned to each possible outcome. The process unfolds step by step, each decision based on the current result. In contrast, continuous time Markov chains deal with processes where changes happen continuously over time, without clear separate steps. An example might be the arrival of customers at a shop. Each new arrival happens at a random time, influenced by the present state, but with no fixed intervals between arrivals. These chains also give rise to the concept of transition probabilities. Transition probabilities are the likelihood of moving from one state to another within a Markov chain. For instance, if you're modeling a customer's behavior in a store, the transition probabilities might represent the likelihood of a customer moving from browsing to purchasing, or from purchasing to leaving the shop. These probabilities form the backbone of Markov chains, mapping out the flow between different states and giving us a way to predict the evolution of the system over time. Another fascinating aspect of Markov chains is the idea of a steady state. In many Markov chains, as the process evolves, it tends to settle into a long-term pattern where the probabilities of being in each state stabilize. This steady state represents the equilibrium of the system, a point where the fluctuations from state to state no longer significantly change the overall distribution. It's as though, after a period of randomness, the system finds a kind of balance. In practice, this concept is widely used. For example, Google's PageRank algorithm uses a Markov chain to rank web pages, where the steady state reflects the probability that a user will end up on any given page after clicking through multiple links. Markov chains also help explain phenomena like the gambler's rule, a classic problem in probability theory. Imagine a gambler playing a game with a fixed amount of money. Each round, they either win or lose a small amount based on a Markov process. Over time, the probabilities reveal a sobering truth. Without an unlimited source of funds, the gambler will eventually lose everything, even if they have a slight advantage in the game. This example underscores the power of Markov chains in modeling situations that evolve incrementally, one small step at a time, where the outcomes hinge on the current state. Now it's worth considering how Markov chains apply to real-world systems. In biology, for example, Markov models help describe the sequence of events in DNA mutations. The future mutations of a DNA strand depend only on the present configuration, not on how it arrived at that configuration. Similarly, in finance, traders use Markov models to predict stock prices, where the future value of a stock depends on its current price, not on the previous fluctuations. In each case, the present dictates the future, with probabilities guiding the transitions from one state to another, like a river winding its way through a valley, shaped by the path it takes in each moment. In summary, Markov chains offer a way to model systems that evolve step by step, with each transition influenced only by the present. Whether we're studying weather patterns, financial markets, or the movement of particles, Markov chains provide a framework for understanding how these systems develop over time. They remind us that, while the future may be uncertain, there's a structure to how things unfold, a balance between randomness and predictability. And in that balance, we find a way to navigate the complexities of the world, one step at a time. The Monte Carlo method, what an intriguing name, isn't it? It conjures image of games of chance in a glamorous casino, and away, the metaphor fits. This method, at its heart, is all about randomness and chance. The Monte Carlo method is a technique for solving problems that might be too complex to handle with traditional mathematical approaches. It works by simulating a process many times and observing the outcomes. Through this repeated sampling, we get a clearer picture of the likely results. It's a way of using randomness to explore uncertainty, uncover patterns, and make sense of things that may initially seem out of reach. Imagine, for a moment, you're standing at the edge of a river, trying to estimate its width. Instead of wading in or measuring it directly, you decide to throw stones across, one by one. By observing how often the stones land on the opposite shore, you begin to approximate the width of the river. A note: that's how the Monte Carlo method works, except instead of stones, we use random simulations to solve problems. It's a bit like running an experiment in a world governed by chance. Each simulation is a step closer to understanding the underlying structure of the problem. What makes the Monte Carlo method particularly powerful is its ability to handle complexity. Some problems are so intricate, with so many variables and possibilities, that finding an exact solution becomes impractical. In these cases, the Monte Carlo method steps in, using randomness as a tool to approximate a solution. It's a bit like casting a net into the sea of uncertainty and drawing out the essential patterns hidden within. The more samples you take, the more accurate your estimate becomes, like sharpening the focus of a lens until a clear image emerges from the blur. The method gets its name from the famous Monte Carlo casino, a place where chance and probability reign supreme. It was first used during World War II, when scientists needed to simulate nuclear processes too complicated for traditional calculations. Since then, it has found applications in fields ranging from physics and finance to engineering and biology. Anywhere uncertainty exists, whether predicting the stock market or simulating the spread of a disease, the Monte Carlo method offers a way to cut through the complexity. It's like peering through the fog of uncertainty and catching glimpses of what lies beyond. One of the key strengths of the Monte Carlo method is its flexibility. It can be applied to problems where traditional methods might struggle, and it thrives in situations where multiple variables interact in unpredictable ways. For instance, consider the task of evaluating financial risk. The future is filled with uncertainty. Interest rates might change, markets might fluctuate, and unexpected events can always arise. Instead of trying to predict every possible outcome precisely, the Monte Carlo method runs thousands, even millions, of simulations, each one representing a different possible future. By looking at the range of outcomes, we can estimate the risks and rewards with greater clarity. What's fascinating about this approach is that it doesn't require perfect knowledge of the system we're studying. Instead, it relies on randomness and repetition to build a picture. In essence, the Monte Carlo method embraces uncertainty and uses it to our advantage. By letting randomness play its role, we gather enough information to make informed decisions, even in the face of complexity. It's like using the movement of the wind to help navigate a ship. By working with the unpredictable, we find a way to chart a course. Another notable feature of the Monte Carlo method is its reliance on probability distributions. These distributions describe how likely different outcomes are within a given range. When running simulations, we draw random samples from these distributions, allowing us to model the uncertainties in the problem. For example, if we're modeling weather patterns, we might use a probability distribution to represent the likelihood of different temperatures or rainfall amounts. Each simulation pulls from this distribution, creating a series of outcomes that reflect the variability of the real world. Over time, the pattern that emerges offers us a clearer view of what to expect. The beauty of the Monte Carlo method is that it works even when the problem is too complex to solve directly. Some problems, especially in physics and engineering, involve so many variables and interactions that solving them with traditional equations becomes impossible. Yet, by simulating the process over and over, we can approximate a solution. It's a reminder that sometimes the best way to understand something is not by trying to pin it down exactly, but by exploring the range of possibilities and seeing where the patterns lead. This approach turns randomness from an obstacle into a tool for discovery. Consider a practical example: calculating the value of pi. Pi, the ratio of a circumference to its diameter, is a mathematical constant that has fascinated minds for millennia. But there's a clever way to estimate pi using the Monte Carlo method. Imagine a circle inscribed in a square. By randomly generating points within the square, we can estimate how many points fall inside the circle. The ratio of points inside the circle to the total number of points gives us an approximation of pi. The more points we generate, the closer we get to the true value. It's a simple yet powerful demonstration of the method's effectiveness. Monte Carlo methods also play a crucial role in optimization problems. Optimization is the process of finding the best solution from a set of possible choices, and it's often used in engineering and logistics. Imagine trying to optimize the design of an airplane wing when numerous factors like shape, material, and air resistance come into play. The Monte Carlo method allows engineers to simulate different designs and test how they perform under various conditions. By exploring these possibilities, they can hone in on the optimal solution, even when the system is too complex to analyze directly. In closing, the Monte Carlo method is a testament to the power of randomness in solving complex problems. It reminds us that uncertainty isn't something to fear, but rather something to harness. Through repeated simulations, we can build a picture of how systems behave, even when the underlying processes are too intricate to grasp in their entirety. Whether we're navigating financial markets, predicting the weather, or solving age-old mathematical puzzles, the Monte Carlo method offers a way to cut through the complexity and find clarity in the face of uncertainty. It's a tool that transforms the unpredictable into something we can understand. Thank you, dear listener, for joining me on this journey through the fascinating world of probability and uncertainty. I hope our time together has provided you with a sense of calm and curiosity, a gentle exploration of the complexities that quietly shape our world. Whether we've touched upon the subtleties of the Monte Carlo method or wandered through the patterns of Markov chains, I trust it's been both informative and soothing, helping you unwind as the evening draws to a close. As we part ways for now, remember the beauty of these concepts lies not just in their mathematical precision, but in the way they offer us a deeper understanding of life's inherent unpredictability. We may never know exactly what tomorrow holds, but through our exploration of probability, we gain tools to navigate uncertainty with grace and wisdom. So, with that, I wish you a peaceful night ahead. Thank you once more for lending me your ears and your time. Until next we meet, may you rest well, and may your dreams be as curious and wondrous as the ideas we've explored together. Good night, and sleep peacefully. Also,